title is Computational Aspects of Mappings, and maybe this tutorial is kind of fitting to start with because on one hand, it deals with topics that are kind of broad and you can apply to a lot of areas in geometry processing, but on the other hand, if we did the work correctly, it should be quite tangible. So let's get started. So the boring definition of a mapping or a map is simply a function between domains or spaces. And let's just go through a quick few examples. Of course, the most immediate example is a mapping of the real line to itself from R to R, for instance, this parabola. Or maybe a more interesting map is of the plane to itself. So we take some textured square and map it using this map. Or maybe this mapping of a mesh in 3D to the plane. Or a mapping between two surfaces. What you see here, we texture the left surface and then use the mapping to transfer the texture to the right surface. So places that have the same letters correspond to one another. You can kind of infer what the mapping looks like from this. Or maybe a cool map from like the sphere to the bunny, the Stanford bunny. Or also we can deform some volume like this volumetric cube into some other form, like this map. And mappings have a lot of applications. So just to name a few that we're going to touch throughout this tutorial, of course, the main one is deformations, where you have some shape, be it like a 3D mesh, a volume, some 2D shape, and you just want to move it around and deform it in a way that's natural or at least distorting in some sense. Another very important application is parameterizations. So parameterization usually just means I have a 3D mesh and I want to map it to the plane, like flatten it, or also like sometimes you want to work with volumes or you want to map it to other domains. But basically what you're trying to do is simply find a good atlas or a chart for your mapping that is assigned good coordinates for each point on the mesh, on the surface. And lastly, a topic that's also very important is, of course, surface mappings, where you try to map two surfaces to one another and find good correspondences between them. So that summarizes our quick introduction. And now let's discuss how we're actually going to compute these maps. So of course, because we're dealing with a computation of maps, we actually need to have some form of discrete maps, because we can't work with a continuous objects in a computer. And while in the smooth case, we think of some smooth surface that we want to map. For instance, in this case, we want to map this smooth blob to the plane. In the discrete case, we're usually faced with the following test. We have a mesh, which is a graph made up of vertices connected to form triangles. And we want to map it. Following the previous example, we want to parameterize it to the plane. And this is actually an illustrative example that gives us a first taste of what a mapping is, so let's follow it forward. So we have this mesh in 3D, and if you can imagine it, this mesh looks like half a sphere. This is its boundary. It's like a dome. And we want to map it to the plane. So what we're going to do is we're going to look at each of its vertices, and for each vertex, we're going to assign the position in the plane. For instance, this vertex vi, we're going to map to this point phi in the plane. And what's important to note is that vi are constant. They're given to us with the mesh that's given as input. And the degrees of freedom we can play with are the variables or the phi where we place each vertex in the plane. Now, having placed all the vertices, we can now extend the mapping to the edges of the graph. And by that, we've actually computed an embedding of the graph into the plane, right? So let's forget about the 3D mesh and focus on this embedding. And more than that, let's focus on a specific type of embedding, which is called Tuts embedding, and it's probably the most classic example of an embedding that you can think of. So, Tuts, I think 1961, gave probably the first embedding algorithm, probably, I'm not sure. And he just gave a simple set of rules to embed a graph. First, we require that each boundary vertex of the graph is mapped to a vertex of a convex polygon in the plane. And just this can be enforced using a simple linear equation. You require that phi I is mapped to some point pi, which is pre-designated. And again, this equation is linear in phi. condition is that each interior vertex lies at the average of its neighbors. And this is called discrete harmonic. I'll explain later what exactly does this name mean. For now, take it for granted. So, to require that each vertex lies at the average of its neighbors simply means that if you look at all these green vertices, the neighbors of the blue vertex, and we denote them as phi j, we now simply write this equation, which basically just means sum up all these green vertices, divide by the number, the point you got, this is the point where the blue vertex should lie. And actually, we can use any set of positive weights as long as they sum to 1 and require that the vertex lies in their average. This is just a way to write a weighted average, right? And again, you can see that this equation is linear in phi. So we have two simple conditions, constraints that we want to enforce. And this leads to a sparse linear system that we can solve easily and get an embedding. And what's cool about this embedding is that, first of all, Todd showed that the resulting embedding is bijective, meaning that the graph edges don't overlap themselves when you create this embedding, which is really not trivial. Like a lot of other embeddings you can try will very quickly begin to overlap themselves. And secondly, what's cool is that this mapping is discrete harmonic, which is an analog of a smooth harmonic. So let's just dive into that for just a moment. So a harmonic function is defined as a function whose Laplacian is 0. And intuitively, Laplacian just measures the difference of a value at a point from the average at its infinitesimal neighborhood. That's one way to formulate it. So you can say that a harmonic map is a map that each one of its coordinates is a harmonic function. And that basically means that if we look at a point P on the surface and its image in the plane, then you can say P is mapped to the average of its neighborhood. And by construction, this is exactly what we did in the discrete case. We mapped each point to the average of its neighborhoods. So this is like, I think, a recurrent thing in geometry processing in general, that you try to find like discrete analogs of continuous settings. And I think in mappings, this is quite something that can be very gainful, because the discrete mappings always try to emulate some continuous notion. And now I'm switching over to that.
Okay, so everyone, let me continue exactly where Noam stopped. So basically, Noam gave you a very simple recipe for computing a very certain type of map. So he gave you instructions of how to map the boundary of the domain, and told you how to set the position of each of the internal vertices. And that's it. And he guaranteed you that you get a map with its properties and so on. And more generally, when we come to compute maps of triangular or tetrahedral meshes, it follows generally follows similar setting. So we have domain. The first thing we do is we say we want to impose constraints on the domain. For example, here that the bottom line, or the vertices along the bottom line of this bar go, for example, to this curve. And then we wish to prescribe the position of the rest of the vertices such that, in a way that something good happens. And we'll discuss that in a second. So for example, like that, or like that, or like that, which all generate different maps that behave differently. And more generally, or to sum that up, when we try to compute maps, many mapping algorithms take the following form. We have constraints we want to impose, and we want to find maps for the position of the rest of the vertices that is good in some sense. So to bring that, or to formulate that a bit more formally, mapping problems can quite broadly be classified as constraint optimization problems. So in these problems formulated like that, quite generally, we want to optimize or minimize an energy, which should be something that makes sense to our application, and we'll discuss that in a second, subject to some constraints which the user usually prescribe. For example, here that this line over there moves to this, transforms to this curve. So let's discuss the energy for a second, which is probably the most important component of map computation. So we all recall that piecewise-linear maps are completely determined by the way each triangle transforms. So, and each triangle, its transformation is determined by its vertices, of course. So it's enough. So we recall that the vertices V completely define the map. So if a triangle with vertices U moves to a triangle, transforms to a triangle with vertices V, this completely defines the map if you do that for every triangle. And a triangle undergoes a piecewise affine map. So each triangle undergoes a transformation, and actually this transformation is a continuation of the transformation of the vertices to the interior of the triangle, which follows this simple formula. So every x undergoes a linear transformation dictated by the matrix Aj plus translation, which we denote here by delta. So since this completely determines our mapping in the piecewise-linear case, we can always look at the energy of a map as defined by these linear matrices, by these linear transformations. And I omit the translation due to the fact that for most interesting energies, we want the energy to be translation invariant. So for the rest of the talk, we can forget the translation and only deal with the linear part of these transformations. So we have an energy for optimizing maps or for computing maps, which is described in terms of the differentials or the mesh gradients, which are exactly these linear transformations. And actually, I think in many or in most geometry processing problems or interesting energies, the energy is always separable, which means that the energy can be defined as a sum of functions acting on each of these linear transformations, on each of these matrices, where this function is the same function for every element. And we'll see a few examples soon enough. So, right, we have an energy we want to minimize. So we want to minimize the sum of f, the same f acting on each of these linear transformations. Now there's a slight problem we just have to dwell on for a second, is that this energy is defined separately or independently for each triangle. So if we simply optimize it, we get like these super triangles because the triangles do not interact with each other. So in a sense, we must impose continuity in the optimization or in the computation of the map. So this can be thought of in two different but equivalent ways. One way to think about it is that our optimization variables, the thing we want to find, is these linear maps, are the AIs, these matrices. And then we just want to make sure that the adjacent AIs, or AIs that belong to adjacent triangles, agree. What do I mean with that? If I have two adjacent triangles that each of them undergoes a linear transformation, I just want to make sure that the vertices here in the left side, these vertices are transformed to the same location, like that, right? And this is simply a linear constraint on the position, on the new position V of the vertices. So if we take the optimization variables to be the matrices AI, we simply have to add an additional linear constraint which imposes continuity. A bit of a different, perhaps, which looks in the beginning a bit more complicated, but is actually more convenient for the actual computation, is to notice the following fact. If we look on the vertices themselves, and we know that the position of the vertices defines the map, we can write this simple relation. So I use the bar over here to denote the centroid. So this basically is done only to get rid of the translation for the simplicity of notation. So I see that if I employ AI, the transformation, on the vertices on the left side, I get exactly the vertices on the right side. So let's do a simple math manipulation. We simply multiply on the right with the pseudo-inverse or the inverse. Ignore the technical details for a moment. which means that the AI, the transformation, is a linear function of the use. Note that the v's, which are the source vertices, are constants, and the target vertices are the unknown. The target locations are the unknowns, which means that this is a linear function of the target vertices, or the target locations. So we linearly express the differentials, or these linear transformations, in terms of the location of the target, or the target location of the vertices, denoted here by U. So if we set the optimization variables, or think of the problem in terms of the optimization variables as they use the target locations, we can express the energy as in this form, which is, again, these f's acting on the differentials, which are in themselves linear functions of our SOT transformations. Target vertex equations. So great, for the rest of the talk, we can assume continuity is already imposed in either one of these ways. It's not really important, that's just technical details. So let's see a few popular energies. So this is a very simple energy. So it takes exactly the form I described earlier. Okay, this is the sum of separate things acting on each of the transformations, each of the differentials. So here we have a weighted sum of the Frobenius norm squared of each of the differentials. Right? So this is a simple quadratic energy. These weights here usually represent the area or the volume of elements in the mesh. And the motivation to do that is to be in some sense invariant to the way in which we decide to tessellate, how to tessellate the domain. So for example, we would like to get the same result if we minimize this energy here, or minimize the same energy over a different tessellation of the mesh, right? This sounds a bit quite natural. And something interesting to note that this thing here is exactly the variational formulation of what Noam showed earlier as the top algorithm. So minimizing this energy, which is called the Dirichlet energy, is exactly the same as doing what Noam described earlier as of how to put the vertices and so on. Great, so just a very simple application of the minimization of this energy would be to map domains. What do I mean here? Let's say we have two domains, the left and the right, and we want to find a nice map between them. When I say nice, I mean map which is projective and behaves nicely and so on. So one common way to do that, which now we'll describe in more detail a bit later, is to first set a common domain which is convex, then compute the map from the left shape or the left domain to that convex domain. Do the same to the right one. In both cases, since we minimize a Dirichlet energy, which is equivalent to employing Tutt's algorithm, we're guaranteed to get a nice map, that is a bijective map. And then we can simply compute a map from the left shape to the right shape by composing the inverse of this map over that map. So the point goes from here to here, and then from here to here using the inverse of the map side, and so on, and we get a nice map that can be used, for example, for transferring this texture from the left shape to the right shape in this paper. And now we'll describe this method a bit more in detail later. So, by the way, feel free to stop me if you have any questions, as long as the questions are not too complicated. Okay, so just a quick reminder. So everyone recalls that an orthogonal matrix is a matrix whose transposition is exactly like its inverse, and it would be a rotation matrix if its determinant is positive. So a rotation matrix just, or orthogonal matrix just rotates triangles. And S would be a similarity simply if it is a scaled version of a rotation. So it means that we have scaling here alpha, which is different than 1, times a rotation matrix. So similarity simply transforms triangles to triangles of the same shape, a different size. And sometimes causes nausea to the person inside. So for rotation matrices and similarity matrices or transformations, we can also compute the closest one. So if we're given a matrix A, any transformation A, we can ask to define what would be the closest rotation matrix for given matrix A. And we can also define S of A, which would be the closest similarity matrix to the matrix someone gave us. So these two operators, we have two operators, R of A and S of A. S of A can be simply computed using the SVD. So as you recall, an SVD is the composition of A into this product of matrices, where sigma is the diagonal matrix. Its diagonal entries are exactly the singular values, which are all non-negative. I guess you all know that. No need to expand. So the closest rotation to a matrix A would simply be taking its SVD decomposition and omitting the diagonal matrix sigma, which is the same as setting all the singular values to 1, which makes sense because rotation matrices or orthogonal matrices have all 1 singular values. Now computing the closest similarity matrix would be almost the same, only we need to multiply the closest rotation matrix by the average of the singular values, which also makes sense because we simply are trying to find something which is rotation in its nature, but has some sort of scale. So let's see how these two concepts of closest rotation and closest similarity matrix can be actually used for mapping computations. So here we define a different energy, which is called the least squares conformal map, which is quite simple. Again, we take a weighted sum. As before, we weigh usually using the areas, and volumes, and so on, for the energy to be geometric. And here in the norm, we look at the difference between AJ, or differential, and its closest similarity, right? So this entire term basically measures, in some sense, the amount of non-similarity in the matrix, right? So we're trying to find a map which is as similar as possible. So a map which is as similar as possible would ideally transform squares to squares, right? Because a map which is the similarity preserves angles and so on, conformality for those of you who know. Great, so you can see that in this result, squares kind of remain squarish. They're of course not exactly squares because the energy is not brought to 0. So let's see what happens in the case, it's quite insightful to see what happens if the energy is actually minimized to the 0, to the global minimum. So let's say the energy equals 0. You see that the energy is the sum of positive things because we're looking at norms. So this basically describes that every triangle has to undergo an exact similarity transformation. So let's say the first triangle, the left top triangle undergoes this similarity transformation, and look what happens to the one next to it. It also has to undergo an exact similarity transformation, and it has to be adjacent to this triangle, so this has to undergo exactly the same transformation. And as we continue on, we see that it has to undergo a global similarity transformation. So all triangles must undergo exactly the same transformation. So this actually fits because we recall that global similarities are exactly the conformal maps in the discrete piecewise-linear case. Okay, so this is quite fine. So this energy, the least squares conformal map, is quite useful mostly for parameterization. So as Noam described, parameterization is the process in which we take a surface mesh and try to flatten it to find parameterization, which allows us, for example, to put a texture on the mesh, on the surface. Great, so we spoke about similarities and rotations or orthogonal matrices, so we can define almost the same energy, only now we take the difference between the differential and its closest rotation matrix. Right? Great, so this term will now measure the amount of non-rigidity of the matrix. So again, here we minimize an energy which attempts to map every triangle rigidly, right? Of course, not all triangles can be mapped rigidly, subject to general constraints. So we'll get something that resembles a rigid transformation as much as possible. So this energy kind of imitates an elastic transformation. It is not elastic in the physical sense, but it kind of resembles it in the way it looks. And it is quite popular energy. For that cause, it is a popular energy for deformation. For example, here deforming that dinosaur from this pose to this pose. So I think it's interesting for a second to notice the difference between as rigid as possible energy and the least squares conformal map, which basically take almost the same form, except for the fact that in one we measure the distance from rotation matrices, and in one we measure the distance from similarity matrices. So you see that the transformations are similar, but not exactly the same. So where's the difference? The difference is that for the least squares conformal maps, squares have the tendency to try to remain squares. While for the as rigid as possible energy, this is not the case anymore. Right? However, on the other hand, you see that this transformation is something you'd consider more physical or elastic or something that makes sense for deformations, and that's why this energy is used for deformations. So we described, I think, the three most popular energies in geometry processing. Let's see for a second how to actually compute them, because we're here to compute them. So the first energy is the Dirichlet energy, which is based on looking at the Frobenius norms of matrices, which are quadratic things, and therefore minimizing this energy basically boils down to a simple least squares. So if you want to minimize Dirichlet energy, all you have to do is backslash, and this backslash in MATLAB. And this, of course, agrees with Noam's description of the Tat algorithm, which boils down also to a linear system of equations. Great. So for the LSCM case, the situation is not really the same, because we have here inside the norm this closest similarity operator. So actually, only for the 2D case, kind of a miracle happens. So let's see what's that miracle. We said that the closest similarity matrix would simply be the U times V from the singular value composition multiplied by the average of the singular values. That seems like something that might be a bit hard to compute, but only for the 2D case, and I stress this only happens in the 2D case, and we'll discuss that a bit more in detail there. There's a very interesting linear decomposition of the matrix A into its similarity part and anti-similarity part. Right? So for the 2D case, we can decompose the matrix into similarity and anti-similarity. And since here we look at the difference between the matrix and the closest similarity, this is exactly the anti-similarity part, which can be linearly computed in terms of the matrix A. So in the 2D case, we also have to simply solve a linear system of equations in order to minimize the LSCM energy. Great. Now, what happens for the LSCM energy in higher dimensions, or for the AROP energy, which suffers the same problem? We cannot compute that in closed form, and we'll need some sort of an iterative approximation. So let's understand for a second where exactly is the difficulty. So the difficulty is that this thing is not very friendly for direct minimization. And the problem lies in the fact that when you look at the difference between A and its closest rotation matrix, you look at the difference between A and these UVs of the singular value decomposition of A, which are computed using the SVD and are therefore non-linear, non-convex. You all know that SVD is not something that takes any closed form. But something we need to notice is that the closest rotation for a given matrix is something that is simple to compute. So if we look at, I don't know, 3 by 3 matrices for the 3D case, computing the SVD of a 3 by 3 matrix is quite easy, a simple linear method. So this actually leads to the following very, very simple alternating optimization algorithm. So So we iteratively do the following thing. First, we compute and fix Rj to be the closest rotation to the transformation of the jth element, Aj. Great, so this is something that is easy to compute using the SVD. Then we go ahead and plug that thing back into our functional, right? And now we have a much simpler functional to minimize. Okay, so this is here functional where Aj only appears here. This Rj is now fixed, basically based on the result of the previous iteration. So we just minimize that. So we can notice that this first step here is a local step because it acts separately and independently on each of the differentials, while this step is a global step that works on the entire mesh and kind of blends everything together. So this algorithm, for that reason, is called the local algorithm, which I think is probably one of the most popular algorithms in geometry processing for minimizing this energy and more recently other energies as well. So let's see for a second how it actually looks or works. So let's say we have this domain here, and we have three constraints over the left column, right column, and some one line in the center, and we want to move that line up. Great, so now we want to minimize the as rigid as possible energy. This does not look elastic in any sense. So the first thing we do, we compute the closest rigid transformation, the closest rotation for each of the triangles. So this looks something like that. That's the local step, which is completely independent for each of the elements, right? So continuity is no longer preserved, and we get that super triangle. The next thing we do, we solve the global step, which is a dispersed problem, because we already fixed the rotations. Now, this step, provided we use the correct representation or add continuity constraints, as we discussed earlier, now gives you a continuous result, which somehow resembles the rotations of each of the elements we got in the previous local step. And we continue that process iteratively, moving between these two steps. And a couple more iterations. And if everything goes well, we get something that looks a bit more elastic than before. Great, so alternative optimization is actually way more general than what I just described for a very specific energy. For example, that work from about 4 years ago called Shape-Up introduced the concept of alternative optimization for optimizing all sorts of energies and constraints on all sorts of different data types. So it can be for point clouds, meshes, polygonal meshes, and so on. So they basically extended that idea to many other cases. And in fact, there's quite a lot of research done to that algorithm we just saw. That would be gradient descent, global local, alternate projections, proximal algorithms are all quite interrelated for quite related to what I've just shown. So keep that in mind. So going back to our energies, we had 3 different energies, and something very interesting to note is that each of these energies can take a very insightful formulation when expressed in terms of the singular values of the differentials. So you all recall that the Frobenius norm of a matrix squared is exactly the sum of the square of the singular values, right? So this energy is exactly like the squared sum of the singular values. The LSCM energy is would be exactly the squared sum or the squared distance of the singular values from the average. And the case of the as rigid as possible energy would be exactly the sum of the squared distances of the singular values from 1, which again also makes sense because we recall that the rigid transformation is a transformation for which all the singular values are exactly 1. And this is actually makes a lot of sense because singular values are very geometric property of matrices. They basically measure the amount by which a linear transformation changes the length of vectors. Right? and this actually inspired quite a lot of work which have tried to define all sorts of interesting energies in terms of singular values. So let's just see a few quick examples. I'm not going to go into actually almost no detail at all. So this work here minimizes this energy in terms of singular values, which attempts to minimize some sort of isometric distortion. This is different type of an isometric distortion, defined it differently, and another one for parameterization, and surface mappings were also computed by minimizing a singular value energy defined in terms of singular values, and another energy, and it goes on and on. So, in a sense, everything we've discussed so far can be can be explained as follows. And forgive me, but this illustration is quite inaccurate, but I think it serves the purpose I'm trying to convey, the message I'm trying to convey. So let's imagine this is the space of mappings, or of all mappings we've discussed so far. So all piecewise linear maps, or all linear maps. So we can cut that space in half and look only on maps with positive determinant, which are maps that preserve the orientation of elements, which are interesting maps because, as you know, we usually want elements not to flip because it is bad. It is bad for applications, it is bad for optimization, it's bad for computations. On the maps we get, it is not physical because usually a small element of matter do not tend to invert or to change its mass to be negative. So positive determinant is good. And within that subspace or set of transformations, we have defined the rotation matrices, or the rotational transformations, and the similarities, which by their definition contain the set of rotations. And usually when we came to compute a transformation, we wanted something nice to happen. For example, we wanted triangles to map rigidity. We wanted triangles to undergo a rotation, a rotational transformation. So this illustration is actually very misleading because these sets we define are actually very, very small within the set of all transformations, and they're actually null sets because they're zero measure within all the set of transformations. So what usually happens when we try to compute maps which are all rigid or all singularity or so on, we get quite different results. And most of the triangles, if not, some of the triangles, if not most of them, behave very differently than what we expect. So triangles, they go transformations which are not rigid, even though we wanted them to undergo rigid transformations. So they may squish, or they may even drift away to the zone of triangles which are inverted. So here we have an inverted triangle, or they can land exactly on zero determinant and give us degeneracies in the computation, which are all bad things. So let's see how this actually translates to something real. So here we computed to as rigid as possible deformation by minimizing this energy. And you can see that here in this area we get all sorts of bad things that happen. The shape intersects itself, and believe me that triangles over there inside become degenerate, or maybe have ellipse, and so on. So in a sense, if you look again at the space of mappings, we have the entire set of mappings, and we have here something we define which is basically a point within that set. And we would like to define something which is bigger than the set of rotations and the set of singularities, but it is still way smaller and controlled in a sense within the set of all transformations. And in several of works related to bounded distortion mappings, we suggested to do exactly that by imposing bounds on the singular values of matrices. Okay, so where's the challenge in doing that? So, as you recall, singular values are basically simply roots of polynomials, right? If you have a matrix and you want to compute its singular values, you have to first look at the product of the matrix with itself transposed, and then compute the characteristic polynomial, which is polynomial of degree, very high degree generally, and then compute its roots, and this gives you the singular values. So the singular values are generally always nonlinear, non-convex, and unfortunately, except for very low dimensional problems, they have no closed form. Yet, in a sense, they're awesome, and we want to work with them. So for example, if you have that information of a person, which is, in a sense, unconstrained information, and you can see that it has a solid face, singular values can allow us to improve its face, improve its life, and have its mind back again. So in a couple of works we did in our group, we suggested and devised methods for imposing singular value constraints, for imposing constraints on singular values, and actually even more than that, computing energy, which are, or minimizing energies, which are expressed in terms of singular values. And the way we suggest to do that is by a sequence of convex optimization problems, which I will explain in a second. So to begin with, we identified that in order to impose bounds or constraints on singular values, it is basically sufficient to impose the simplest type of bounds on singular values, which are bounding them between two constants. This can be thought of imposing a constraint on the singular values to lie within that annulus, right? Which has inner radius small gamma and outer radius capital gamma. Great. So one observation we make is the upper bound is a convex constraint or a convex expression, while the lower bound is a non-convex constraint, which we illustrate here as the outside of a ball. Right? So the outside of the ball is, of course, not convex, because if you connect two dots from both sides, the line that connects them crosses the empty part in the middle. Great. So in a sense, this is our problem. We want to deal with that non-convexity. And why would we want to do that? Because as we all think or used to think, convex is good. Why convex is good? Because convex comes with guarantees, and convex is easy to optimize. But is it so? So I want to stop you for a second and convince you that convex is good, but not always. So let's see an example. This set here, okay, so all matrices whose this quadratic form is non-negative for all x. It is exactly the set of all positive semi-definite matrices. So this is, of course, a convex set, a convex cone of positive semi-definite matrices. And this is an easy cone. In what sense is it an easy set? For example, let's say I give you a matrix, 100 by 100 matrix, and I ask you, is that a positive semi-definite matrix? Does this matrix belong to this cone? Can you answer that question? Anyone has an idea how to answer that question? I have an idea how to answer that question. I simply go to MATLAB, compute the eigendecomposition of that matrix. If all the eigenvalues are non-negative, very good. That matrix is positive semi-definite. Great. So let's make a very simple modification to this set. All I do here is instead of requiring that expression to be non-negative for all x, I now require it to be non-negative for all positive, non-negative x's. For all x, those entries are all non-negative. So you can imagine that this set is also convex, right? Because we didn't really do something weird here. We only added that linear inequality. So believe me, that set is convex. It is actually called the set of copositive matrices. And this set is extremely difficult. What do I mean by extremely difficult? Let's say I give you a 5 by 5 matrix or a 6 by 6 matrix, which is very small. And I ask you again, tell me whether that matrix is a copositive matrix or not. You generally cannot answer that question. So just the process of determining whether a matrix belongs to this set or not is an NP-hard problem. So now we're all kind of not happy because I convinced you that convex is not good, but convex is good. For certain classes of convex problem, or certain classes of convex problem are very good. So let me give you just a few examples. If I define a convex set by linear inequalities, which leads to linear programming, that's a very good set of convex problem. If I define a convex set that is based on such equalities, saying that the norm is smaller than a constant, this is also a nice set which defines the second order cone programming. And if I define a convex set by positive semi-definite matrices, this defines a very nice set of semi-definite programming problems. And these sets have kind of a hierarchy, so linear programming is subsumed by SOCP, which is in turn subsumed by SDP. And these sets of problems are very nice because they come with all the nice guarantees of convexity, and they have efficient methods for their optimization, or efficient solvers, efficient optimization engines. So we had that non-convex set, and we said we want to find a convex way to handle it. So the first, or the primary approach to doing that would be to convexify it, right? To find a larger set, which is convex and contains this set. So in this case, this is useless because we simply close the whole matrix and we get the entire space of matrices. So just doing a convex relaxation here is pointless. What we suggest to do instead is to find a convex cover, which is to try to find convex subsets of this set and possibly to cover it with it. So I'm not going to go into all the details for the interest of time. I'm just going to give you the highlight of what we do. So we know the following very simple fact that if you take a matrix A and you split it, decompose it into its symmetric part and anti-symmetric part, which is quite simple, it is sufficient to impose a bound, a lower bound of the singular value of the symmetric part of the matrix to ensure that the same bound holds for the original matrix itself. Right? Great. And by the way, this only goes this way. The other way around is not true. So, and this constraint can be formulated using or realized in SOCP in the case of 2x2 matrices, and realized using SDP in the case of higher dimensional matrices. So, I'm not going to give you any more details. If you're interested, just look at the work or talk to us afterwards. But I would like to spend a moment emphasizing the differences between the 2D case and the higher dimensional case. So in the 2D case, the closest similarity matrix has a closed form expression, as we saw earlier, which is no longer true for the case for the higher dimensional case. This also incarnates in different form by saying that in the 2x2 case, in the 2D case, rotation matrices commute, while in the higher dimensional case, rotation matrices do not commute, and let me try to demonstrate that for a second. Probably won't do it correctly, but I will try. So let's say this now undergoes a 2x2 transformation rotation. So it rotates in plane. So if I take it, I don't know, 90 degrees to the left, and then back, it's exactly the same as taking it 90 degrees to the right, and back to the left, which means 2D rotations commute, right? Now, let's try to do it in 3D. I'll probably do it wrong. So let's say right now, the first turn turns like that. Okay, and then I will turn it along this axis, which is this thing. So watch now that the cap goes over there, and the sticker goes to the bottom. And now I will try to do the same thing in the opposite direction. So that would be first rotating it like that, and then rotating it like that, which gives you a completely different result, right? So rotations in 3D do not compute. I hope I've convinced you. I'm not sure if I convinced myself. Try to do that again at home. And to be more concrete, in 2D, the singular value values have a closed form expression, which I won't be able to show you here in the interest of time. But in higher dimensions, the singular values are the roots of polynomials of degrees 6 and higher. And as we all know, polynomials of that degree do not have a closed form solution for the roots. And eventually, this led us to the SOCP formulation in the 2D case and to the quite different STP, semi-definite programming realization in the 3D case. So let's see just a simple example of what this higher mass of bounding singular values is at all good for. So let's say we have that cube and we want to grab its corners and move them around and get a deformation like that of the cube. So you can notice that every element of the cube now undergoes a linear transformation or an affine transformation. And we can look at the ratio between the maximal singular value and its minimal singular value, the max of each element. So the maximal singular value is the maximal amount of stretch that an element underwent, and the minimal singular value is the maximum amount of shrink. And the ratio basically defines the change of aspect ratio, right? Great. So we can look on all elements of the mesh, check the change of aspect ratio at each point, the local change of aspect ratio at each point, and then try to minimize the maximal change of aspect ratio. So among all elements, we want to try to find the one that underwent the largest change of aspect ratio and minimize that. So in a sense, we can think about it in the following way. We look at the histogram distortions, the histogram of changes in aspect ratio, and we would like to push it down as much as possible. So as to get a map which is the least, gives you the least change in aspect ratio, which is also known as the most conformal map. So this has been studied quite a lot in 2D. Actually, maps that minimize that quantity are well defined or well characterized in 2D, but in 3D only neither is known. However, using our complexification approach, we can compute or approximate these maps in all these cases. So you can see here 4 example maps. For each map, you have a volumetric thing that is deformed, and we have 2 cuts that allows you to see the interior of the volume, and you can see that the map is quite nice. It is quite conformal. The elements do not change their aspect ratio too much, which can be seen by noticing that squares kind of remain squarish. And these deformations are very smooth and very regular, although we did not do anything in particular to impose that. And that's another example of map, these maps which are called extremal Quasiconformal maps. And with that, I will go away and let Noam continue.
Okay, so originally at this point we thought we were going to have a break, but seeing that it's a relatively large cloud, we're going to continue forward, and I hope we can just finish a little earlier even. But what I want to say about this part is that Shahar gave you some introduction to the algebraic notions and like linear algebra and optimization of that's in computational mappings. And now I'm going to touch topics which are more geometric, and also I think most of them are modular. So if you feel like you're zoning out, you start thinking about Eurocup or something, it's totally fine. You can catch up like when I start a new part, and I think like each piece stands on its own. So the first thing I want to talk about is injectivity, which is a very sought after property of mappings. So a quick reminder, injectivity simply means that the map is one-to-one, and in the bottom you see a mapping that takes this blob to deforms it in a way that's not self-overlapping. So of course this is an injective map. But the map G on the top, of course, makes the blob overlap itself, so it's a non-injective. So let's see what can we say about injectivity of mappings. So if we take this triangle with this handsome fellow in it, and we try to map it affinely. As long as the determinant of this mapping is non-zero, we may skew the triangle and squish it, but this mapping is still injective. And of course, only when the mapping becomes singular or the determinant becomes zero is this mapping non-injective. And even when the determinant goes negative, this is simply a flip of the triangle, or we're reversing its orientation, but still this mapping is injective. So let's move forward. What happens when we have two triangles and we have a piecewise affine map of the two? So imagine we take this blue vertex and we start pushing it to the left. And as we start pushing it, at some point, this green triangle is going to flip over to the other side and reverse its orientation. And this is exactly the point in which this piecewise affine map becomes non-injective. And it's at the moment when the sign of the determinant of the two triangles is different. And clearly you can see this non-injectivity if we take this small neighborhood around the middle edge at the left, and we look at it and how it is mapped in the right, you can see that it's clearly self-overlapping. So this mapping is not injective. So what we can infer from this is that injectivity requires a consistent orientation of all the triangles. Well, the question is that sufficient to ensure that the piecewise affine map is injective? And the answer is no. I can show you a very simple example. So imagine we take this one ring of triangles, and now I map it thusly. So clearly, all the triangles in this example maintain for orientation, none are flipped, but still this mapping is not injective, exactly at the center vertex. So what can we say about this? How can we prevent this type of non-injective mapping to happen? Well, it's easy to see that if we take a small loop around the center vertex and consider how is it mapped by this mapping, you can see that at the bottom, this loop intertwines and loops twice over the center vertex when it's mapped for a total angle of 4 pi. And at the top, it still loops only once and gives us an angle of 2 pi. So this gives us our set of conditions that if we impose, we can get a locally injected mapping, which basically means in a small enough neighborhood, the mapping is injected. If we make sure that the determinant is non-zero on all the faces, then inside each face we're going to be locally injected. We ensure that all the determinants have a constant sign. Arbitrarily, we can choose it to be positive. Then we're going to ensure that we're locally injective on each edge. And lastly, if we can make sure that the sum of angles around each vertex sums up exactly to 2 pi, we're going to be locally injective on each vertex. So Shahar already showed you, basically, and in the last part, how to make sure that the determinant of all the elements is positive. We can do it using the bounded distortion spaces, other methods, controlling zero values. But we don't exactly know how to control this last part, how to make sure that the sum of angles remains 2 pi. And that's actually like a slightly more difficult problem because you cannot attack it immediately through linear algebra. But you have like simpler ways to attack it. For instance, what we can note is that the winding around the center vertex is always some multiplicity of 2 pi, right? It's either 2 pi on the top, 4 pi on the bottom, or you can make these triangles loop around themselves like 3 times and get total angles on the 6 pi. But the main thing to note is it's always an integer multiplicity of 2 pi, and this gives rise to a very simple idea. We can simply initialize our map to be something that is globally bijective, for instance, using that. And namely, then the angle sum around each vertex is going to be 2 pi. And now we can start deforming the flattenings continuously while avoiding flipping any triangles. And as we do this, remember that we just saw that the angle sum around each vertex is some integer multiplicity. And because the angle sum is some continuous function of the vertex positions, we cannot actually flip and change it from 2 pi to 4 pi instantaneously because it's a continuous function. And that entails that while we deform the mesh, we're guaranteed to preserve this sum of angles of 2 pi around each point. So this is just like to give you like some quick idea of one way to do it. There are probably many other ideas, and But while it's open injective, it's not global injective. You can see there are these many overlaps in the mapping, and things are not like sitting separately. And this is because local injectivity is a much more softer property than global injectivity. It's necessary to ensure global injectivity, but it's not enough. But nonetheless, this is a very important property on its own. And I will discuss this a bit later. But what can we say about global injectivity? The entire mapping is injective. Well, again, as the first result, I think, is that gave us a very simple algorithm to ensure that to get an bijective embedded. And also, previous works from our lab also proved that if the boundary map is injective and you have no flipping of any of the triangles, then the mapping is guaranteed to be globally injective. Even if the boundary is non-convex or quite elaborate, as long as the boundary is injective and you avoid flips, for instance, using the boundary distortion spaces that Shahar mentioned, you're going to get a globally injective map. So the question remains, how do you make sure that the boundary doesn't overlap and the boundary map is injective? Well, the simplest solution is to simply fix the boundary, like we did in that. But this causes a very constrained problem, because the entire boundary is fixed, you cannot really optimize the map too much and lower the distortion. Another option is to prevent the boundary from overlapping explicitly while optimizing. For instance, in this work by Smith and Schaefer. But the problem is that this leads to a very hard optimization problem. And while it's very cool to see the boundary resulting shape, it's very hard to optimize. So, in a short while, I'm going to show you a free method to actually let the boundary be free, but still to ensure that the resulting map is bijective. So now, let's just go over a few small topics that relate to geometry processing of mappings. Well, throughout this talk, I've been discussing parameterizing disks. So in this case, you see David's head, and you can imagine that the bottom of the neck is cut open, and because of that, it's like the mesh has this shape of a disk, and now we can simply stretch open the neck and flatten David's head, and we all know how to do that. But what happens if I actually close the bottom of David's neck? And now we have like a topological sphere, and we want to parameterize the sphere. So how do we do that? Well, clearly, we cannot just map it as is, because you cannot map something that is of sphere topology into the plane. You cannot induce an homomorphism that way. So we need to cut it open or something like that before we map it. And that's the naive solution. We can simply reduce spheres to disks. And the way we do it, you can imagine our mesh as the sphere on the left. And imagine I've drawn these lines on the sphere. And now, imagine I take a pair of scissors, and I proceed to cut the mesh open, for instance, through this red curve. And once I cut through this red curve, I actually duplicate it into two curves on two sides of the cut, one on the left side and on the right side. And now I'm left with something that's, again, topologically a disk. And we can apply this method immediately, right? We can take David's head, and you can see I've drawn these cuts, made the blue and red lines, and proceeded to cut it open through these lines. And now we can parameterize it to the plane. But you can see that this parameterization is kind of unnatural, because, well, the cuts are kind of arbitrary. I don't really have a smart way of designating where to put them, nor there is any smart way to know where to put them. And as a result, you can see that like David's face is like squished to the right side, and something not nice is happening. At the top there, everything is kind of skewed. And we want to do something more natural. So an idea that's maybe more fitting is, instead of using a fixed boundary, using a periodic boundary. And what I mean by periodic boundary is very simple. So all we need to do is to ensure that the two sides of each cut are related by 90 degrees rotations, for instance. So if we take some point VI on the cut, as I said, when I cut the mesh open, I duplicate it into 2 points on the two sides of the cut, phi I and phi prime. And now we require that these 2 points are related by 90 degrees rotation around this yellow corner point. that is exactly what's called a cone manifold. This is simply a manifold with some identification of vertices on it that gives it some other topology. And you identify sets of vertices as corresponding and relate them by some rotation. And this is something that's well used in geometry processing, and I think Marcel is probably going to discuss it in greater detail today. I'm not going to until they haven't asked him, but I'm guessing. But this gives rise to an extension for TAT that we saw earlier that worked for disks. Now we can actually use it for things that do not have a boundary. And we're just going to do the same thing that TAT did originally. We're simply going to impose a set of linear conditions that give us a bijective parameterization, but this time for spheres. So the first condition is the boundary condition, which I just described earlier, that the vertices are rotated copies of one another. And again, note that this is still a linear constraint. It's slightly more elaborate than the previous ones that we saw in the original TAT, but nonetheless, it's a linear equation that we can formulate. And what's nice to see is that once we have this periodic boundary, you can imagine we take copies of this mesh and glue them to one another so as to create this tiling. And actually, we can continue this tiling until we conceptually tile the entire plane. Of course, what we actually compute is just one of these tiles, but we need to keep in mind that this basic tile enables us to tile the entire plane. And now we can impose the second condition that we want, which is exactly the same condition from the original TAT embedding, that each vertex is harmonic, and that the mapping is harmonic, meaning that each vertex lies in the average of its neighbors. So for vertices lying inside our tile, it's very easy. It's the same equation from before. I just look at its neighborhood and say I want it to lie exactly at the average of all its neighbors. It's very easy. And for vertices lying exactly on the path, I can do exactly the same thing. The equation is kind of elaborate, so I won't go into it, but I just need to imagine how the tiling looks and then impose the right conditions, but it's still a linear equation. And as a result of this computation, what we get is actually a harmonic tiling of R2. So you can imagine like an infinite mesh that's harmonic everywhere. And just like classic TAT, we get a global injective mapping, which means that this mapping to this one tile is globally injective. And that's our work from previous year, which is called orbifold TAT embeddings. And the idea, what we've shown in the paper, is that if we require these two conditions, that the boundaries are rotated copies that can create this basic tile that can tile the plane, and that the resulting tiling is harmonic everywhere, then this gives rise to a sparse linear system that has a unique solution, and the resulting embedding is guaranteed to be injective. And again, all you need to do to solve this equation is just exactly as the original TAT to solve a sparse linear system. So just a word, why does it work? It's because we're using orbifolds, which are basically just a cone manifold, as we saw earlier, but with the special property that can actually create these tiles that can tile the entire plane. And something even more magical about this embedding is that if you cut the mesh differently, you're still going to get the same embedding. To understand what I mean by that, so here you can see I've changed the cuts that David had to create these two different embeddings, each one resulting from different cuts. And they may look different at the beginning, but if we start using them to tile the plane, you can see that what happens around the yellow point, it's exactly the same image. And if I were to continue and tile the entire plane, we would get exactly the same tiling. So basically the cuts don't mean anything, and this embedding is kind of seamless. But to give you maybe a more concrete understanding of how the orbifold looks like, I can show you this image. So imagine I started from David's head, and then I took the embedding I've just shown you, and I printed it with a regular printer. And now I went ahead and folded it over the diagonal, and then folded the bottom piece, and then I flipped it over and folded this right piece. And in the end, you can see that I've gotten this closed shape that's again a sphere. It's like a flat sphere, or like you can imagine it is like this pillow with 3 corners. And that's the way people used to like to call cone manifolds also, like talk about pillows, because you can imagine an object that's basically flat. You can open it and flatten it to the plane, except for a few points where you have this cone singularities, the points around which the rotations happen. So So that's just an image to keep in mind that an orbifold, while it's like kind of an abstract creature, it's still something that's very tangible when you imagine it as this pillow, and that's actually the thing we're embedding in. All right, so let's put that aside for now and move on to discuss surface maps, which basically is the last big topic of the day. So surface maps have a different goal than all the mappings we've discussed so far, because so far we've been talking about mapping into Euclidean spaces. Now we're in a slightly different setting. We're given two surface maps, M and N, and a core set of corresponding landmarks, which you can see as these colored spheres on the two meshes, which are colored according to their correspondence. And what we want to output is a mapping between the two surfaces, which is bijective, meaning that it's one-to-one and also onto now. And it has high quality. For instance, by some metric, it has a low isometric distortion. And of course, it maps the landmarks correctly. And we visualize this mapping, as I said earlier, by texturing the left mesh in this case, and using the map to transfer the texture to the right mesh, so we can understand what's happening. So the main question when attacking this problem of surface mapping is, how do you want to represent a surface mesh? And the basic idea that most people do is to use some common domain. Most of the time, and what we do always, is use parameterizations. And let me now elaborate on how that works. Basically, imagine our two meshes as these two spheres. And the user has given us a bunch of landmarks. And now, we first connect the landmarks with curves and proceed just as we did earlier. Now you can imagine what we do is we extend the landmark correspondence to the curves. So for each curve, for each point on the left curve, we associate the corresponding point on the right curve on the other side. And now, exactly as I showed you earlier, we can cut the mesh open and map it to a disk in the plane. We proceed to do the same thing to the other mesh. And now we're going to impose two conditions on these two parameterizations. First, the two parameterizations are bijective, again, one-to-one and one-to-two. And that we make the boundaries identically. And what I mean by that is that if I take the right boundary and overlay it on the left boundary, we get exactly the same image. Well, with this process, we just defined a bijective map between the two surfaces. And to see it, take some point on the left mesh, map it using phi, and now consider the exact same point on the other embedding, and map it back using the inverse of psi. So you see we've just computed a map F, which is simply the inverse of psi composed on phi. And this mapping is a homomorphism, meaning it's also continuous and its inverse is continuous. See this, just take a curve passing through the cut. Of course, when you map it to the plane because of the cut, it gets split apart. But if you look at the inverse map psi, it exactly glues it back together. So this mapping is also continuous. The question is this good enough? This is a very simple method, and again, as we noted, people have been using it for a long, long time. But, and let's try to see how it works on a real example. So we take our two meshes, and we map into the plane. We use stats embedding, which of course gives us both the things we want. It's bijective, and we can prescribe the boundaries, so we can make sure that the two boundaries have exactly the same image in the plane. And now, if we look at the distortion of these mappings, you can see that it's quite high. And as a result, the mapping doesn't look that good. You can see that, for instance, there's this blood stretch on the neck, and something bad is happening on the face also. And the main reason that this happens is because the fixed boundary prevents us from doing anything to reduce the distortion. So one way of taking this is, for instance, by letting the boundaries move. By this, we can reduce the distortion. So let's think what's happening in this case. If the boundaries don't overlap, we're good to go because we can still ensure by our theorem from earlier that the mappings are bijective if we make sure that no triangles are flipped. And of course, we can make sure that the boundaries are identical. We can simply add it as a constraint to some optimization of them. And as a result, we're still going to get a bijective surface map between the two surfaces. The problems begin when there are overlaps, as we saw earlier. And of course, in this case, we cannot define a mapping because psi is no longer injective, and we cannot invert it. So here's the point where local injectivity comes into play. What we've shown in our group in our work from 2014 is that we can still recover a bijection, and these embeddings define a bijection if we're locally injected. So local injectivity, while it's a much weaker property, can still lead to very interesting results if you use this. But even though we let the boundaries move, we haven't solved one last problem in this case. And that problem is that the cuts affect the mapping. So if we zoom in on the right-hand side, you can see that the mapping kind of warps around the cuts, as you can see. And this should make sense, right? Because what we did when we cut the mesh open, we actually prescribed correspondences on these cuts. So we're kind of forcing the map to do something that not really, the user just gave us a few landmarks and said these landmarks should be mapped to one another. He didn't say anything about cutting the mesh or making some correspondings along these cuts. And this is something that's unnatural. So what we want to do is get a seamless result, meaning that these cuts that we produce when we parameterize don't affect the map. Well, I've mentioned the word seamless just a few slides ago, right? We saw that orbifolds are seamless. Embedding into orbifold is seamless. When we do this, the seams don't have any effect. So actually what we can do, and I'm just going to give you the high-level image of it, is we can define maps by embedding into orbifolds. We can simply take two meshes and map them into some orbifold we're choosing. And this, exactly as the previous parameterization, defines an embedding, but surface map between the two surfaces. But here, the cuts have no effect on the mapping. Basically, we get a result that's completely seamless and well-defined between the surfaces, and has no relation to the way we're going to decide on how to cut the meshes. And that basically wraps up, I think, our part, and I'm just going to summarize quickly. Well, there are a lot of things we didn't touch, but basically, most of the time with this piecewise-linear, addressing the problems of mapping through piecewise-linear maps is very powerful, although it's so simple and tangible. And you can see in a lot of cases that it actually approximates continuous objects. For instance, in this case, you can see an approximation of the uniformization of this mapping of the cat into this triangle. And of course, you can go beyond piecewise-linear map. For instance, you can discuss methods that don't even work in meshes, like meshless, which use thin-bed splines or stuff like that, which in this case were used to deform this left image into this right image. Or other things that you can consider using some higher order FEM. For instance, this deformation of a capital card subdivision surface. But basically, I think the insights that piecewise-linear maps give you are enough to be able to tackle all these tasks and to understand how you should approach them. And I think the big questions that are open now are thinking of faster optimization. A lot of the tests that Shahar mentioned sometimes are require long optimization times, and this is something that at least our lab is very interested always in making things move faster. And coding with non-Euclidean domains, like the surface maps, is also something that's very far from being a closed problem. The main thing that's missing is that we parameterize the two surfaces. And when we do this, we're computing maps that may have low distortion in the parameterization, but we can't guarantee that the mapping between the two surfaces themselves has low distortion. And that is because we don't take into account the actual metric change between the two surfaces, only what's happening between the surfaces and the plane. And of course, one can always come up with new distortion metrics. It's not like there's one good metric for distortion that's proven to be the best distortion metric. People constantly come up with